So this is the Operator Framework SIG meeting for August 17th, and we're just waiting for everyone to join us. A very tight agenda, so we're only going to start about 2 minutes after the hour, I guess. I'll wait, and Shawn Hurley, our first guest speaker, is here, and he's going to be talking about the Ansible operator that he's working on, or maybe has ready. We'll get an update on that today. And our other co-chair, Rob Szumanski's just joined. Dan Kozlowski will be talking, Dan's from PlanetScale, so he's going to be talking about the Vitess operator today. And we have one other guest I don't see has joined us yet. Evan Cordell is going to talk about the operator Lifecycle Management, but people are just joining and coming in the room, so we'll see as how people come in. So this is, if you haven't previously joined the Google mailing list, please do so. I see Evan now. Hi, Evan. And we'll just, hopefully you do most of our communication through the Google mailing list on the Google groups, pretty active. And we also have a Slack channel on OpenShift Commons, if you would care to join that as well, that we can hook you up with. So Rob, do you have any quick words of wisdom before we get started with Shawn's talk? And Shawn, do you want to start sharing your screen? And let's get set up.
Yeah, I was just going to say thank you to everybody for joining, and don't have too much to say other than I was going to put a link to a new operator from Redis Labs to operate Redis clusters, which is really cool, and I believe they released it earlier this week or late last week. So if you want to take a look at that, I'll throw a link in the doc and the chat.
I'll try and get the Redis guys to come to one of the upcoming meetings and talk about it too, so that'll be great. All right. So if you're coming in late, please add your name to the agenda. Our first guest is going to be talking about the Ansible operator, Shawn Hurley, who's a Red Hatter. So I'm going to let you just get started, Shawn, and we'll roll on.
Okay. Hi, everybody. I'm Shawn Hurley. I work at Red Hat with a team of guys working on the Ansible operator, which will be eventually part of the Operator SDK. So really quickly, we just kind of want to talk about why we chose Ansible as for the operator. One of the really powerful things about Ansible is that we're using the new Kubernetes modules that will manage Kubernetes resources. It makes it really easy to template Kubernetes resources just using Ansible. So you can do all of the Ansible things that you can do and also manage Kubernetes resources how you have come to expect with other tools. We also are able to use Ansible Runner, which allows us to run a playbook or a standalone role. It means that we can reuse roles and just run them right from Ansible Runner, as well as a playbook. It also gives us structured output, which will help us help an operator author manage their status of their resource. And then we also have some helpers that will allow us to kind of hide the details of knowing about owner references and things and metadata of a Kubernetes resource. So I'll just quickly go through the design of what we got started with. So at the top here, we have a user going ahead and creating a custom resource where they will define their application state. And then the Ansible operator will be watching for that resource. Yeah, the Ansible operator is based on the Operator SDK, and so it has all of the go watch logic based on the Operator SDK. And then it has a config file which maps the group version kind of that resource to the Ansible playbook or role. The Ansible playbook or role is then run whenever an event happens on that custom resource. And that playbook or role will actually create the application state in the cluster. So that will create all your resources that you need and allows you to manage your application using Ansible. And like I said previously, we're using the new modules. So those really help out. So we're going to quickly talk about that configuration file that I just talked about, where it maps the group version kind to a playbook or a role. This is really the heart of how this works, is you now define your CRD's group version kind, and you tell it which playbook you want it to do. You package that up into the container, and then the Ansible operator now knows what to do when the events come in for that resource. So next thing we can talk about is how are we going to hand parameters to Ansible based on the spec that the user defines for their resource. And so what we've determined is that the spec key values can map well to Ansible's extra vars, and these will allow us to say a user defines their spec, and then we tell Ansible what those user-defined parameters are. The Ansible operator also will take a first stab at managing the status for the operator author. As the operators are supposed to own statuses, we thought it was important that we do this, and because of Ansible Runner, we're able to get structured output about what is happening in the Ansible run and surface that to the user who only wants to look at their CR that they created. So that's what we're doing here. So as you can see, like green is the user-defined stuff, and then the blue stuff is what the operator is managing. So we'll go back to the design overview with a little bit more added. And you can see here that I've added that the Ansible operator is actually writing back to the custom resource the status based on what we've determined from Ansible Runner. We can also see that the events are coming back from the from Ansible playbook or the role back into the Ansible operator so that we can do this. So you might be asking, how do you end up using the Ansible operator? One of the ways that we envision using the Ansible operator is using a base image, and then you're only responsible for creating that config file, creating a custom resource definition, and then writing the Ansible code that you need to do the logic and work that you want it to do. So the basic idea is that the Ansible operator is already packaged up and into a base image. You just use that base image when you're building your own operator, and you copy in these files, and then the Ansible operator knows where to look for the config file and will be able to run. And all you have to do is write the Ansible code. So moving on, we can go to the demo that I have hopefully working. And so right now, I just have a Minikube cluster up and running with my CRD already installed. And so I have here this folder, which is effectively going to be what I'm calling a BusyBox Ansible operator. This BusyBox role has a single task, and its job is to create a BusyBox pod, and then just run this while true echo out a message to the console. So
Shawn, can I get you to make your font a little bit bigger?
Yeah.
Those of us with eyeballs, older eyeballs.
Nope, that didn't work the way I wanted it to.
Sorry about that. People are squinting.
Command Shift plus or equals.
Yeah, that's much more readable. Thank you.
Okay. Yep. Sorry about that, guys. So this is the task. What it will do is, like I said, it will just print out a message that we define from the CR, but it also has a default. So because Ansible already has default. So the other thing that we probably care about is the config file that we're using. So right here, you can see that all it is a mapping of the group version in kind and into the Ansible playbook path that we've have here, and we can see the playbook is just a task that will import a role. So let's, and we can also look at this Docker file here, because that's the other thing that matters. We can see that we're using our base image. We're going to copy in the BusyBox role. We're going to copy in the playbook, and we'll also copy in the Ansible config, the config file for the Ansible operator. So we're going to go ahead and just deploy this operator. I already have, okay, sorry about that. So we can see that it's spinning up right now, and we can go ahead and get the logs of this guy. All right, so that's running. What we'll do now is actually create one of those CRs for CRD. We can see that we actually got our first event. What is taking so long? There we go. So now Ansible's running. You can actually see the Ansible output right now. And we have our BusyBox pod running. So we can go ahead and see what that guy is doing. As you can see, it's just printing out hello world. Let's say we wanted to change that message. What we could do is just edit my CR. So we just edited it, and we should see the Ansible operator kicking off any minute now. There it goes. And so we'll look at that new one. And you can see it's saying new hello world. And so if you remember, we just took this role and we're starting to use it. And that role really didn't have anything to do with, let's say, owner references. So as an Ansible operator author who's just writing Ansible, you might not know that you need to set an owner reference to be able to do garbage collection. And the Ansible operator actually has a mechanism to help you with that. So we can actually put that that owner reference in for you based on the resources that you create when you run Ansible. So what we can do is actually just go ahead and delete that CR, and we should see that it actually ends up deleting all of the resources that were created for that CR. So that's the demo. I also want to talk a little bit about the hybrid use case that we're calling it. What we're thinking is that because the Ansible operator code will be a part of the Operator SDK, you can actually use the Operator SDK, the Ansible operator code, the same way you would the Operator SDK code. This means that you can actually compose pieces of Ansible that you might want to run from a Go operator that you're writing to give you more flexibility so you can do things that you would like to do. So that's one other way that we're planning on allowing people to use this. So if you want to learn more, this is like a pre-alpha application. We're still very much in the early stages, and it will be PR will be submitted in about 1 to 2 months to the Operator SDK to get this fully baked in. Right now, it's in Waterhole Ansible Operator. There's a link right there for you guys to go to. And most of our team is hanging out already in the Kubernetes Slack, in the Kubernetes Operators channel. If you have any questions, or as I think Rob already added to the chat for this, you can email the group at Operator Framework via Google Groups. So I will open it up to questions and stop sharing.
All right. Does anyone have any questions for Shawn and the team that's sitting there patiently looking for your feedback? While we're waiting for that, Evan, if you want to share your screen and get set up to do your talk, that'd be great.
I'm going to say one thing about the goal for this is really exciting, which is to match the technology skills that an operator author has. And so Golang, is a great language, but can be a little bit impenetrable, and folks might not have skills. Or if you're in a more ops focused versus dev focused team, you shouldn't have to learn a programming language to make an operator. And so this is really going to bridge those gaps where you can start with Ansible. If you do want to start calling some custom Go code, then you can kind of level up to that, and then maybe you'll fully transition to Go, or maybe not. So that's really exciting. And so this joins our Helm operator kit, and that works much the same way, where you just use this base image. You don't have to produce anything. You just add a few files in, your chart, and you're good to go. And so this will operate much the same way, and which is really exciting to make this a wider audience that can produce operators. Which is really exciting. And then the other thing that Ansible brings to the table, which is really, really cool, is that there's this plethora of Ansible already written out there. And so you can connect, orchestrating external hardware load balancers, for example, all the things that you can do in the Ansible ecosystem with an operator and into your Kubernetes cluster natively, which is super, super exciting. So thank you for sharing that demo. And I'm really excited to get this in the SDK in 1 to 2 months.
Yeah, thanks, Rob.
All right, then. If there's no other questions, or if there are questions, ask them in the chat, and we'll just let Evan introduce the Operator Lifecycle Management.
All right, hi, can you hear me?
Yes, we can.
Awesome, thank you. I am Evan Cordell. I am an engineer at Red Hat on the Operator Lifecycle Manager team. And so I wanted to sort of go over some of the philosophy and architecture and implementation, and then do a demo of OLM, because we do get a lot of questions about it. What is it? Why do I want it? How does it work? And I don't think we've really put together anything for public consumption that sort of lays it all out there for you very well. So I'm going to start right at the basics, but I'll go through quickly. So I know we're in the Operator 6, so everyone has an idea of what an operator is already. But for us, for Operator Lifecycle Manager, we really think of an operator as a Kubernetes application, a Kubernetes native application, I should say. And by that, I just mean that it's an application whose interface is the Kubernetes API. And so all of the assumptions around OLM are all around this idea that you are interacting with an application via the Kubernetes API and orchestrating one via the Kubernetes API. I was going to put a picture of Jack Sparrow, but I wasn't so sure about the copyright issues there. But so like we all have this idea of an operator as a set of control loops that watch CRDs, and that's all well and good. And you need those things. But as far as we're concerned, that's all implementation detail of this concept of extending the Kubernetes API. And if Kubernetes comes out with better tools for doing that in the future, we'll still keep up with those in the same exact way. So we know what an operator is. What is operator lifecycle? Well, I'm going to propose this definition that the operator lifecycle is the definition or specification, the installation, the resolution, by which I mean dependency resolution, the upgrading and the automated upgrading, and then the removal of operators. So these are all the responsibilities of the operator lifecycle manager, are defining and managing these different aspects of an operator over its lifetime in a cluster. So what are some of the goals of the operator lifecycle manager? This is what we're trying to provide with the piece of software called OLM. We want to give you an app store-like experience for discovering and installing operators. So what's available to you and what will work when you run it on your cluster, and then also simplifying the installation of an operator down to just a single kubectl apply or a single click in a user interface. The other aspect is automated upgrades. This is some philosophy that we've carried over from CoreOS Container Linux, Tectonic. We know that there's value in updating things automatically because we can ship out fixes to any problems as soon as we know about them. So we want to bring that philosophy into operators as well. Another aspect which probably doesn't get a lot of light is that operator lifecycle is designed to be a framework for building rich and reusable user interfaces. And this is both, again, through the CLI and through the UI. And I'll go into some of the details of how we do that later. And then package management and dependency resolution of operators. Ideally, when you're writing your own operator, you don't need to vendor in 15 other operators just to get yours up and running. We have lessons around how dependency resolution can work from other ecosystems, and we want to take those lessons and apply them to operators as well. So that's some of the philosophy, why we're doing this, what we're trying to get out of it. Let's go over the actual architecture. At a high level, right now, OLM is defined by two separate operators. We call them an OLM and a catalog operator. That's not terribly important. What you need to know is that one of them manages this object called the cluster service version, and that's essentially our package manifest for an operator. And the other operator, the catalog operator, manages these objects that we call catalog sources, which have virtual objects of packages, and then subscriptions and install plans as well. I'll go into exactly what each of those is, but I wanted to emphasize that we have a layered architecture where one thing has very specific responsibilities, which is just the cluster service version, and then another operator has a different set of responsibilities and overlays those on top of the other. So what is a cluster service version? This is our specification file for what an operator is and how it should run. It is 100% analogous to something like a depackage definition or an RPM if you're talking about operating system dependency management. It's also perfectly analogous to setup.py if you have a Python project, or a brew formula if you're using homebrew for Mac. It's the definition of metadata about how to install and run and orchestrate a piece of software on the underlying system. Specifically, we have a set of like textual metadata, things like description, who created it, where did it come from, how do you get support. That's fairly common among package managers. But specifically for Kubernetes, what do we need to define an operator? We have specifically a deployment spec, could be a set of deployment specs, but these are literally defining the pods and deployments that will be running the operator software itself. And then aside from that, the only information we really need to know is the CRDs, because the CRDs define that interface for the operator in Kubernetes. So we say that each operator can declare that it owns a set of CRDs. These are the ones, this is essentially an operator declaring that to the OLM framework that it will be responsible for the lifecycle of particular CRDs. And then there's a set of required CRDs, and this is a list of CRDs, not that the cluster service version will own, but that the operator will interact with in some other way. The rest of our dependency management is hung off of these two concepts of owned and required CRDs, because CRDs are the interfaces. For each of these things, we have what we call descriptors, which are essentially indexes into the CRDs. It's somewhat similar to some of the newer features in Kube, like the, what do they call them? The additional printer columns in CRDs, where you go into an object and you give some additional metadata about that. So this is how we drive some of our UI, and this is how we drive some of the CLI interaction as well. So the OLM operator is responsible for, within every namespace, managing the set of cluster service versions that exists. So for the most part, those will be independent operators, but I wanted to call out what happens when you are in the upgrading state for an operator, in which you have two cluster service versions that define the same operator, but at different versions. Some of the metadata that we collect for operators is which one it replaces. So this gives us a chain back to an older version of an operator. And then OLM manages the lifecycle of those two operators during the upgrade process. So it either patches or force replaces the deployment and migrates resources to the new version, and then GCs the old version. So that's essentially the only responsibility of the OLM operator. The other operator, which we call the catalog operator, which has nothing to do with service catalog, is responsible for these other resources. The primary one is the install plan, and the install plan Similar to our analogy for cluster service versions, the install plan is analogous to using yum or apt for orchestrating packages on an operating system, or pip for if you're using Python with a setup.py file. I also wanted to call out that the install plan is also analogous to various lock files that you find from various ecosystems, because it takes a high-level desired user state and translates that into a ideally immutable set of references that we can apply to other namespaces and get the exact same set of things installed. So an install plan, like I said, has an input that's essentially just the desired CSVs. You can have multiple install plans for a namespace, or you can have multiple CSVs defined in an install plan. This triggers the operator to go and find whatever CSVs and CRDs it knows about, whatever definitions it has. So these are not things that are installed in the cluster yet. And then it writes out the definitions of those into the status block of the install plan. And then another control loop waits for install plans to be completely resolved and then applies those resources into the cluster. So where does an install plan find the CSVs and CRDs? We have a set of objects called catalog sources that define what CSVs and CRDs are known, and then organizes those CSVs and CRDs into packages and channels, which is just an organization mechanism for saying, for example, these 50 CSVs all are installing the etcd operator. So we'll call that the etcd package. And then within that set of 50, here's a chain of 20 of them that are the alpha channel, or the beta channel. So this is just a way to collect and organize all of the definitions of things that are available to a user to install. And then once we have those two things, we have an additional object called a subscription, and subscriptions signal to the operator to check a catalog source frequently for updates, and then whenever an update occurs, to create a new install plan for that object. So this is our full sort of graph of objects. If you're subscribed to a package, for example, etcd, you specify a package in a channel, that points to a catalog source. So our operator goes and looks at the catalog source for any updates. Whenever it finds an update, it creates an install plan with the new versions of the CSVs defined. We have another control loop looking for new install plans. It sees that there's a new install plan with a new desired CSV. It resolves that from any of the catalog sources that it needs to talk to and writes those back into the status of the install plan. Then we take those resolved CSVs and CRDs and actually apply them to the cluster. And once that point is done, everything else is handled by the OLM operator. So there will be a giant set of cluster service versions in a namespace. Some of those might be new, some of those might be removed, some of them might be upgrading from old versions, and the OLM operator handles all those migrations for you and also creates the CRDs themselves. So you end up with a state in your namespace where you have all your CRDs defined. These are all of the new APIs and interfaces that you can use via kubectl or the CI. So now I'm going to flip over to a live demo of this. I have a namespace. This is an OpenShift 311 cluster. I have one catalog source right now, and it has two packages defined. We happen to have just one channel at the moment. When I create a subscription, I am generating a subscription for the etcd package from a particular catalog source and then telling it to track a particular channel. Create that. We have a UI for it, but it has actually created an install plan in the back. The install plan was created by the operator because of my subscription. In this case, it did automatic approval, so the install plan is immediately applied. We also have manual approval, which requires a user with write access to go in and manually approve an install plan before it creates. And then we specify the specific cluster service version that we want. And then in the status block, it actually goes and puts the definitions that will eventually be applied. In the UI, you can go and see that in this case, this particular cluster already had these particular etcd API versions installed as CRDs. And then the one thing that wasn't existing in the namespace was the actual CSV, and so that was created for us. So if I go back to the operator page, I can see that this is representing the etcd CSV installed, and I can go look at the YAML for that. And so the etcd defines a set of owned custom resource definitions. The etcd one does not require any other, so it doesn't depend on anything else, but it does describe the CRDs that it uses. So for example, here is a spec descriptor. So these are the descriptors that we use to drive the UI. This says that if you go into an etcd cluster object and you look at the spec.size path, you can expect it to be of this particular type. And this particular type is, for us, a pod count object. It has a description here, but we can go into, I can go and create an etcd cluster. And once I do that, I am driving the UI. This is generated based on that descriptor. So this is saying that the size is a pod count. And so I know the UI has this widget that shows me I can edit a pod count for a cluster size. I can increase the size to 5 pods, and that gets translated back into the YAML in the backend. So this gives me a way to organize resources and then have insight into what's actually happening in my cluster, while also giving me that abstraction layer of here's an etcd cluster object. Behind the scenes, it ended up creating these pods. It should be spinning up a fourth and a fifth as it's adjusting to my cluster size of 5. But we know that these are the objects that it's creating based on the etcd cluster. And if I go in and I delete the etcd cluster myself, it will eventually GC all of the related resources for me. So that's what when Shawn was talking about the owner references, we rely pretty heavily on that. I think I've probably gone way over time, so that is my general overview of OLM. I apologize that it was relatively rushed, but I hope that I can help with any questions.
Well, that was a really good and quick overview. If there's some questions, that would be great. And if not, you can ask them in the chat while we're setting up for the next topic. But yeah, that was really well done. And also ask questions on the Google group as well.
Hey, Evan, can you describe the workflow of just an end user that needs to interact with this? I just want to get an etcd database, a Mongo database, a Redis database in my namespace, how that all kind of works.
The ideal scenario is that there's some persona split between an administrator and a user. And so the administrator would go and set up namespaces with the operators installed for you. And then as a user, you just go in and you'll see, you'll have RBAC access to create an etcd cluster, and you just go in and create one. And that's all the interaction you have to deal with. So it's up to the administrators to set up, things like subscription policy, whether or not a particular namespace should be updating constantly or not, that kind of thing.
Gotcha. And I guess that's one thing that you didn't cover in your presentation is there is an idea of access control built into this using just this RBAC, but if you can create CSV from those other objects, then that's how you manage this.
Correct. Yeah. So part of the driving ideas behind having everything just be the kube API is that we get the RBAC for free, basically. And we get owner references and garbage collection for free.
Cool. And then you've got you could have a CI system that's just making etcd cluster objects or whatever app you're trying to model.
Yep. I think B2 of this presentation will involve building an application that depends on one of these services.
Cool. Looking forward to that. Thank you so much.
Thanks.
Cool. So next up, we have Dan Kozlowski. I let you pronounce your last name. And from PlanetScale is going to talk about his Vitess operator. And let him introduce himself and what he's been doing, and And I'm just going to tell them, make sure your font size in terminal is a little bigger, because I can already tell it's kind of small. Perfect.
I tried to increase the font size in my editor, which is what we'll get to. But yeah, so my name is Dan Kozlowski. I am the lead engineer at a company called PlanetScale. We provide support for an open source project called Vitess. First thing I wanted to do is sort of go over a little bit of what Vitess is before I jump into our operator. And then what we did here is we built a few versions of Kubernetes operators. And so I called this the tale of two operators, but there's actually like 4 of them. And I'll get into why we did what we did, as well as a few lessons we learned and a few challenges that we're currently facing. But first things first, since I don't know how many people may be familiar with Vitess, it is a database that was developed at YouTube to help Google scale their MySQL deployment. It's a sharding layer on top of a native MySQL database, and this is its architecture. So what it is, it splits a single database into a number of shards. Each of those shards has a number of replicas, and it gates each MySQL process with a Vitess process that we call a VT tablet. And then it provides a gateway, which looks like a normal MySQL server, to a client. So at the end of the day, you have a gateway layer that is horizontally scalable. You have a sharding layer behind it that can have as many shards as you want. And you have a control plane that is in this picture, that's VTCTLD and the lock servers. And this sort of all works together to give you what looks like a single MySQL database, but is actually in the background a lot of machines working together to provide that functionality. So that is Vitess. Some interesting things about it is because this was developed at Google, it was developed to run on Borg, which is the inspiration for Kubernetes. So this has been running for years in something kind of like Kubernetes. So when we took a look at really making it run well in Kubernetes, it was a pretty natural fit. It's now been developed for almost 8 years to work in that environment. So when we asked ourselves, why should we make an operator for this? The reasons why we would make an operator is because it's really close to actually just working like we expect things that run off of operators to work. Everything has been designed to sort of fit together and scale independently. And there are a lot of different components that need a lot of different configuration options based on how you do it. And a lot of that can be abstracted away into a very simple cluster architecture. Also, because it has all these various components and various layers, you need to do more than just bring up containers. So you can get a mostly working Vitess cluster just by using straight Kubernetes manifests, but there are a few steps that have to be taken before you spin up certain components, and then after you spin up certain components, to really make sure that everything can talk to each other. So in that case, it's a prime candidate for an operator, since it's really close to just straight Kubernetes deploy with just a little bit of stuff on top. And in fact, this project was used, Vitess was used to demo a few other, I guess, operator technologies. So there is a metacontroller based operator for Vitess, and there are Helm charts for Vitess, and all of them work pretty good. So at PlanetScale here, we said, well, why do we even need an operator if there is this metacontroller out there? So why would we choose to go with the Operator SDK? We looked around at what we wanted to do, and these are really the reasons why we chose to go with make yet another operator. So when we are talking about running a database in production, we wanted to do more than just provision it. We also wanted to handle lifecycle events. So if you update your version of MySQL, we don't just want to bring down all your database servers and then turn them all back on. There's a sequence of events we want to follow, and a rolling deploy wouldn't necessarily do things in the right order. So we knew we needed a little logic there. We also wanted to be able to handle what I have called the deep state, and that is things like your schema inside your database. To a lot of the other technologies, there is no visibility into actually what's going on inside the database. So when it comes to things like doing DDL transformations, if we wanted to assist in that, we were going to need something that actually had very fine-grained control and was very extensible. And then the last reason why we decided to go with the Operator SDK was for code reuse. So the way we have our project architected, we have a component that takes configuration from Kubernetes by the Operator SDK. It actually passes it off to a non-Kubernetes specific engine, which will then does actually all the lifecycling events, and then that gets passed back to a Kubernetes provisioner. So that little middle block, which actually does all of the configuration, sets command line parameters, and does the ordering of events, that can be reused for other things that we do here at PlanetScale. So we had a compelling reason, and we evaluated the technology, so we went ahead and we built the operator. Version 1 was a real quick and dirty solution. We took the cluster itself and we just transliterated the state of a Vitess cluster into a CRD. We used the most basic state reconciliation that there is, in that we just use the name collision protection that Kubernetes offers to make sure that we're not reprovisioning things. Elements in our operator had deterministic names, so when we tried to create them the second time, we just got a already exists error and went about our business. And because of that, we were able to pretty much eliminate all the internal state. And that was one of our first design goals, was this operator should be completely stateless. It should come up, given a CRD, it should just provision that cluster directly. So this was the CRD that we came up with, and it's a direct transliteration of what a Vitess cluster looks like. So in Vitess, there's this concept of a cell, which is a failure domain. If we were running in AWS, this would be an availability zone, or even a region. And then key spaces are actually your database. Key spaces have replicas, or key space have shards, which is the actual splitting of your entire database into various parts. Then each shard has a list of replicas. So we just wrote all that down. It was very straightforward. And then processing this, we could actually spin up a Vitess cluster very easily. So we made a few slight modifications to add in secrets and to add in the ability to specify your database. But I'm actually just going to page down through this, and you can see one of the problems that we ran into. Still going. So that was our first version of the operator in the CRD, and this actually works really well. We wrote some Python scripts to generate this CRD, and this one is a 64 shard cluster, and this can do several 100,000 queries per second. And provisioning it is just a matter of having the physical resources up and running in your Kubernetes cluster, and then you can get a very high performance database off of it. So that was version 1 of the operator. So we built that, deployed it, started doing some tests with it, and talked to the Vitess community about what we had done, and quickly decided that we needed a version 2. So we went through and we decided to make some improvements. In talking with some of the members of the Vitess community who had built sort of like version 0 of the operator, who had built the Helm chart and the meta controller based operator, we decided on a few initial improvements. So the biggest change and the biggest sort of improvement over that original CRD is incorporating the selector pattern wherever we can. And this is something that I think you'll see a lot through operators that people have made. So the place where I think the best example of it, if you look at the Prometheus operator uses what I will call the selector pattern for actually defining the service selectors. So you can put in as many different service selector manifests as you would like, and then you just have the Prometheus operator give match labels to actually provision the Prometheus server. So we went and incorporated that into the Vitess operator. It's a very good fit for us since you can define key spaces and shards independently of your Vitess cluster. So improvement number 1 was to take all of the shards and all of the key spaces and all the cells, so the 3 sort of components that put together a cluster, and turn them into their own CRDs, and then add the ability to have a selector which can just select those. So that took our extremely large CRD and turned it into something that looks like this. And so now we had a number of CRDs that had these selectors on them. And there was much rejoicing, right? Because that solves a number of problems. You can have different components that are defined sort of independent of each other. I can now change my cells without changing my cluster, and I can let all that propagate through. Where this really becomes great is I can actually define the rest of my cluster with key spaces and shards to exist in a cell, and then I can just duplicate that entire deployment in another cell by just provisioning another cell CRD. So that was the first improvement we made. The second one was sort of, once we did that, we realized we had only moved the problem around a little bit. You still had to do a lot of definition to get a Vitess cluster up and running. So for improvement number 2, we decided, well, how about we also add defaults? So instead of having to define all of your CRDs, you can give some defaults and let the operator define the CRDs for you. Sort of do parameter expansion inside the operator instead of explicitly having to generate all of the shard information and load each of those into the operator. We could just give a sane set of defaults and say how many of those things we wanted, and then let the operator create them for us. So this would be if you decided that you wanted to have a replica, a MySQL replica running a specific container, listening on a specific port with a specific TLS secret, you could just define that container profile once and then tell the operator, I want each of my shards to be running 10 of these replicas, and then the operator would spin up 10 of these replicas. This was a really good exercise for us as we went through the second CRD because it made us be very explicit about how we were going to configure things and where the configuration points were. So when we have to define the configuration points, then we can go through and make sure that we have flexibility in actually defining the cluster. We can say if we wanted to do half of the cluster defined explicitly and half of it expanded from defaults, we wanted to build that in. So that made us then go through and think about how we were going to be able to do that. At the end of that whole process, we ended up with a cluster that can look like this. So that 64 shard cluster that from our initial CRD can actually get collapsed down into this. This would be a cluster definition with 64 shards, 2 replicas per shard in every cell that was labeled super awesome cluster. And here I only have one defined, that's US West. And then if I decided that I wanted to spin up a data center in US East, I would just define the cell for US East, label it correctly, and the operator would expand my footprint into USDs as well, following my defaults. The third improvement is one we actually haven't made yet, and this is our current challenge that we're having. The improvement that we are currently working on is reducing the amount of calls we have to the Kubernetes API. It turns out that when we get these extremely large clusters, we found that we were making a lot of calls to the SDK functions, so SDK create, as well as a lot of functions to get the state of running containers to make sure that we weren't duplicating things. And then internal to Vitess, there is our Vitess control plane, and we were making a lot of calls to the Vitess control plane to check on the state of shards and key spaces and cells. And that is making our reconciliation loop take several seconds, like 40 to 50 seconds. And that was providing problems. So we wanted to make sure that we could reduce that. And that's currently what we're in the works of doing. And we're trying to figure out how we can make sure that we're reconciling correctly so that when an outage occurs or something happens to the resources, that they're getting reprovisioned in short order, but then also not bringing down the API server because we're making so many API calls. So that is sort of the third improvement that we are currently working on. And I know on the mailing list, there has been some chatter about this specific topic, since in addition to just concerns about stability, there was also concerns about cost and other things to consider when we are really instrumenting these operators that are making a lot of automated calls back to the API masters. So those are the improvements that we made for version 2, and then looking at version 3, we're evaluating if we could do some of these things with the Operator SDK, which sort of go beyond what you could do with just straight Kubernetes deployments. So online schema transformations are a big one for us. A lot of people may be familiar with the tool Ghost from GitHub. That works really well with Vitess, and we want to make sure that with an operator, it's a great opportunity to just make that even more seamless so that your schema transformations can be completely automated. Also doing things like cross Kubernetes deployments. Maybe not something that everybody would like to do, but if you have a globally distributed Kubernetes footprint, Vitess was built as a globally distributed database, so it would be, we would want to be able to deploy in different data centers around the world and make that as easy as possible. So right now, the path that people have been looking at is running multiple Kubernetes clusters and then just orchestrating on top of that. And since we're running effectively a Go program, we have options on how to coordinate across Kubernetes deployments. Another great thing, which I actually think I just saw in the OLM operator, is I have it here as chat integration, but really it's human intervention. So when events occur, like upgrades or lifecycle events, don't do them without approval. And that is something that, especially when you consider databases and where they sit in your application stack, the idea of requiring human approval is something that a lot of people are insistent upon. So again, because we do have a lot of integration points, we can do chat integration, or we could do a ticketing system integration so that you can actually give approval before events are taken. And then the last thing, sort of Vitess specific, is auto resharding. Since it's a sharded database, you can expand the size of the cluster as big as you would like, and that's something that we can also do with the operator. That's got problems with other style of operators because it is a multi-stepped, sometimes multiple day thing that happens. But since with the Operator SDK, we can maintain state in a global lock server or in some external entity. We can do those big multi-day lifecycle events. So that is the story of our two operators, of sort of our path through creating them. Vitess is an open source product. So if you want to take a look at it, it's vitess.io. We hang out on Slack. That second link there is the link to join our Slack. Stop in, say hi. And then, like I said, I work for a company called PlanetScale. We're providing support commercial support and features on top of that open source product. Find me as Koz on most of the places that I lurk.
All right. Well, thank you very much. Tiny bit of echo. Not sure why that is. But if there, is there any questions for Dan or Koz? Okay.
I have one really quick.
Go for it.
Just to clarify, I'm curious if you actually saw any problems with the operator bringing the API server down?
No, we have not. The problem that we've been running into now is just the performance of when we get really big clusters and when we get a lot of operators running off the same cluster, it slows the operator down. So it just takes too long for the operator to run its reconcile loop. I'm concerned about bringing the API server down, but we haven't actually managed to do that yet.
Hey, this is Shawn. Just a quick note, I think that the controller runtime design story in Operator SDK might be an issue worth watching for you. I think this should help with that problem because I believe the controller runtime will start to use an informer cache to do Git and list requests, which will probably significantly help in this regard. But that's just a guess from a guy, so I don't really know if that's true.
I had another random question. How are you running the etcd cluster that you're utilizing?
We use the etcd operator. Well, it depends. So for the etcd cluster that's associated with each cell, which is the failure domain, we just provision that with the etcd operator. We ask that you load the etcd operator before you load our operator so that we can just we can provision the etcd CRD. The global one's a little bit different since Vitess can span Kubernetes clusters. The etcd operator doesn't quite work there. So we just have some custom code to spin up etcd, cross-region etcd cluster.
How is that synced between the 2 clusters or 3 clusters that you were running or that you would run?
So the etcd, the global lock server is the coordination point for multi-cluster communication. So Vitess knows how to run in completely isolated data centers, and there doesn't need to be any synchronization between them. But that global lock server does need to be accessible by each cluster and does need to maintain state for all of them. That's why we provision it outside of Kubernetes. We could also, early demos that we did, we actually just picked one Kubernetes cluster, made that the special cluster, and then had its etcd server be the global one, and then just made sure everybody could see it.
Gotcha. That was a strategy we took under Tectonic's multi-cluster stuff that we were testing, was like make one of these clusters special. Other than that, they all look the same. Yeah. Looking forward to a demo of it next time, maybe.
Yeah, now I feel like I should have, every time I've done this, I've tried to give demos. The demos do take a little bit longer, and I wanted to make sure we had time for questions.
Yeah, no worries. A YouTube video, maybe.
Yeah, that would be wonderful. We can give you a longer time to do a deeper dive too once you're ready for that. So we're sort of almost at the end of the hour, and I just want to respect everybody's time. The next meeting is going to be on September 21st. If you can answer maybe on the mailing list or otherwise, if this format for the meetings is working for people, working for me because I'm learning a lot. But if you wanted a different format or if there are any requests, suggestions, or anyone wants to volunteer to talk about their efforts around this, creating an operator and share their best practices, let Rob or I know, and we'll give you the podium because I'm tired of hearing my own voice. And I love to hear your voices. And again, just really try and utilize that the mailing list and the Kubernetes operator channel. And we'll just keep these conversations rolling. And we're looking forward to, if you're not already listed in the awesome operator repo, post it there, because that sort of builds some awareness of what you're doing, and we'll look forward to getting more of your stuff out there and ready for production use. Any other words of wisdom?
I would say great demos, great presentations. Thank y'all for putting those together. Super awesome, and thanks for joining.
Carol. I will post the notes and the videos shortly, probably in a bit of a raw format, because I'm going on vacation for the next 2 weeks. Be edited, but they'll be on the mailing list and available.
Thanks, everybody.